Hi folks, let's start our second class in our Materials for Photonics and Applications course. In this class we will talk about glasses. Glasses are everywhere. Windows, glasses, optical fibers like this one made here at our laboratory. We will define glasses, main definitions, properties and characterization. Mainly focused in optical properties, since we are interested in photonic materials. So let's do that. Do not forget to answer the quizzes. Good work. Before starting, as usual, please take free of charge some more images from our country. This is Rio de Janeiro, the land of carnival and football. These are images of the new Maracanã Stadium. Our football temple was completely rebuilt for the Football World Cup that was held in Brazil last year. I must say that we have terrible memories about that World Cup. With this link, you can see a short YouTube movie showing the Flamengo supporters in Maracanã. Flamengo is one of the main football teams in Rio de Janeiro. It's amazing. Take a look at it before starting to work. So let's come back to the real world. Let's then talk about glasses as amorphous materials. Let's try to define glasses upon some experimental observations. Do you recognize this figure? Let's make here our first question of the quiz number 2. What is this? What are these circles? Those of you with ages under 30 will never recognize this. Those of you older than that perhaps will recognize this old result from an X-ray diffraction experiment. There you have here a typical diffraction pattern obtained for a glass, and here you have a diffraction pattern obtained for a crystalline samples. Let's talk about that a little bit more. But what is that? Crystalline, amorphous? Let's start by talking about crystalline samples. In the description of a crystalline material, we need a unit cell, that is, the building block of a crystal. From the assembly of the building blocks, we will end up with the spatial coordinates of all atoms. The organized assembly of the unit cells defines what we call long-range order. Diffraction techniques are in this case very useful. X-rays, neutrons, and electrons are diffracted by the crystalline structure. The diffraction pattern can be solved to the 3D description of the structure. Do you remember this from your undergrad course? These are the crystal systems. There are only 7 different types of unit cells that can fulfill the three-dimensional space: cubic, tetragonal, orthorhombic, rhomboedral, hexagonal, monoclinic, and triclinic. And these are the 14 crystal lattices, the Bravais lattices. They show how atoms occupy unit cells. The so-called lattice points are theoretical points in the 3D space. It's important to stress here that point positions may be occupied either by ions or ions groups. They show the packing of unit cells, the basic network over which the crystal is constructed. We will mention many times in this course diffraction techniques. The images in this slide shows diffraction of visible light by diffraction gratings, a transmission diffraction grating at left and a reflection diffraction grating at right. It is in fact one commercial CD. The channel structure of a commercial CD diffracts visible light obeying Bragg's law, since channels width have the same dimensions of the order of the visible light wavelength. This link is the link for a short YouTube movie showing how a CD works. This is the well-known electromagnetic spectrum. The small range highlighted is the one our eyes are sensitive to. It is really narrow, isn't it? Take a moment to imagine what the world would be if we could, for example, see from the infrared to the UV. This is indeed a philosophic note. The world is not what we see. But coming back to our main subject, the X-rays wavelength lie in the range of the order of interplanar distances in crystal structures. Therefore, X-rays are diffracted by crystal structures. Rainbows are the result of the sunlight diffraction by water droplets in the air. This beautiful image was registered in Iguaçu Falls. We have already shown you some images of this astonishing sight in Brazil. So, we may say that crystal structures are 3D diffraction gratings. Bragg's law is shown here. It gives the wavelength that will be diffracted as a function of the interplanar distance and the diffraction angle. Just to remember a little bit your undergrad course, these images show how X-rays are produced in the X-rays tubes that we have in our diffractometers. A metal target is the target for accelerated electrons. This high-energy shock leads to the ejection of electrons and X-rays from the targets. Each target will eject X-rays with a specific wavelength. The wavelength of the copper K-alpha line, for example, is 1.5406 angstroms. In practice, if instead of a single crystal we have a powdered polycrystalline sample, the diffraction of a specific family of planes of crystals, randomly oriented, will occur as shown in this scheme. A diffraction cone will be defined. Each family of planes will display its respective cone. A Debye camera is a device used for registering power diffraction. They practically do not exist anymore. In these devices, the detection of X-rays was performed by a photographic film placed all around the sample. After some time of exposition, the film was removed. And this was the result. The film was marked by the diffracted X-rays. By measuring the diameters of the cones and knowing the dimensions of the camera, the diffraction angle could be determined. Bragg's law gives us the interplanar distances. We had a camera like that here in our institute when I was a student, some weeks ago. The analysis of a diffraction pattern could take some days of boring work. The mineral cristobalite is a high-temperature polymorph of silica, meaning that it has the same chemical formula, SeO2, but a distinct crystal structure. Low and high-temperature quartz, cristobalite, and tridymite are the four silica polymorphs we know. These images show the ion positions in the unit cell, the unit cell filling by the ions, and the connectivity of the SeO4 tetrahedra that builds the cristobalite structure. This is a picture I took from Wikipedia. It shows cristobalite crystals forming from an obsidian glass. We will come back to the obsidian glasses later. For the moment, keep in mind that these crystals are formed from the glass matrix. This figure shows the relative stability of the different silica polymorphs as a function of the temperature. The interesting point for us here is that these polymorphs are all built from the very same tetrahedral SeO4 unit. The differences among the different structures may be explained by the tetrahedral connections. Coming back to our diffraction patterns obtained in the old Debye camera, this is a typical crystal pattern. Several diffraction cones are observed, each one related to a specific atomic plane. And this is a diffraction pattern obtained for a glass. That is, there is no diffraction cone. Only a broad cone can be discerned. This is an interesting picture I brought from a paper published in 2006 in one of the most important journals of the glasses area, the Journal of Non-Crystalline Solids. In this paper, authors take crystalline lead germanate submitted to a high-energy ball mill. X-rays diffraction patterns were obtained for the initial crystalline materials and also after 3 stages of comminution. You may observe that after 400 minutes, no crystal pattern is observed anymore. Only broad lines are observed. The same broad lines are observed for a sample obtained by quenching a melt. Quenching a melt is in fact the oldest method man developed to prepare glasses, as we will see in a moment. Coming back to the paper, the interesting point here is that by using a mill, you can amorphize a crystal. The problem here is that I don't know if this word amorphize exists. Some of you can help me telling me if this word exists or not, okay? What I want to say is that the sample was transformed for something crystalline to something amorphous under the action of the mill. This process is being possible. It's not the rule, it's an exception, I must say. Explains, for example, why the surface of the moon is covered with glass. Did you know that? The continuous meteoric impact and bombardment by interstellar charged atomic particles over billions of years formed glass samples there. This news came some days ago. Last June 8, NASA in US has identified glasses at the surface of Mars. This can be our second quiz question. How do NASA scientists were able to identify glasses at the surface of Mars? Take a look at this link and try to answer that question. With this, we arrived at the first very important experimental conclusion. Glasses are amorphous materials. Of course, amorphous here must be stated together with the method you have utilized. In this case, we'd better to say glasses are amorphous to X-rays. In routine X-rays diffraction, a few percent of crystalline phase could not be determined. You must be aware of that. You always should add which technique you use to state that a sample is a glass. As early as 1932, Zachariasen, working with the new technique developed at that time, X-ray diffraction, he tried to explain the absence of diffraction patterns for some samples. He sketched a 2D scheme where, with the very same structural unit, one could construct either a 2D crystal that is displaying long-range order or an amorphous sample that is displaying no long-range order. These are the figures taken from the original paper published by Zachariasen in JACS in 1932. You will find that paper at our website. It's interesting that Zachariasen wrote, "It is somewhat difficult to illustrate the principle in drawings because of the three-dimensional arrangement. I have therefore tried to make use of the two-dimensional analogies." Remember, it was 1932. Drawings should be made by hand. Anyway, these drawings of the so-called Zachariasen random network became universal. In any textbook or revision about glasses, you will find them. Perhaps it is, together with the nuclear Rutherford atom, one of the figures most reproduced in science. Zachariasen images are well reproduced, as are these images. At least for us Brazilians, these are images that we have in our minds. As I told you before, did I? We are 5 times champions of the world. By the way, we are the only 5 times champions. Italy and Germany are just behind us with 4 trophies each. This is also Brazilian culture. But stop with football. Let's come back to the famous Zachariasen schemes of the 2D crystalline and glass structures. Here you have the 2D crystal and the 2D glass, both with the same 2D building block. Remember, 2D because Zachariasen could not draw a beautiful 3D scheme in 1932. Well, this paper was published in 2012 in Nanoletters. These guys took graphene as a lab bench and deposited a thin film of silica to obtain a 2D glass supported on graphene. The 2D nature of the material enabled the first atomic resolution transmission electron microscopy of a glass, producing images that resemble the Zacharias' original 1932 cartoon model of 2D continuous random network glasses. The study identifies the glass as silica formed from a bilayer of SiO4 tetrahedra without detectable covalent bonding to graphene. These guys claimed that, by accident, they demonstrate a new class of 2D glass that can be applied in layered graphene devices and studied at the atomic scale. In this figure, taken from the paper, you have the Zacharias drawings at the top and microscopy images of 2D crystalline and amorphous silica supported by graphene. The scale bar is 5 angstroms. The similarity between them is amazing, isn't it? E and F images as fast Fourier transform of scanning transmission electron microscopy images from crystalline at left and amorphous regions at right. Also in 2012, these other authors presented a similar work. This time they used ruthenium as substrate. Images are as impressive as the images of the previous paper. Zachariasen is also there. You can find both papers at the school website. Okay, so far we have seen that X-ray diffraction can be used to define a glass as amorphous materials. Let's talk about another experimental observation. Let's take a look at some scans obtained in differential thermal analysis or differential scanning calorimetry. In general words, in both techniques, you heat your sample in a furnace and you have the register of any thermal event, exothermic or endothermic, occurring to your sample as a function of the furnace temperature. Here you have some typical DTA or DSC scans. In red, you have what you should obtain if you have a crystalline monophasic sample. As you heat the sample, nothing happens until it melts at Tm, the solid-liquid first-order phase transition. The black curve is what you observe for a typical glass. The initially solid and amorphous sample is heated until a certain temperature, where the sample changes from a solid to a supercooled liquid. This transformation is not a real thermodynamic phase transition, since you are dealing here with metastable materials, but it resembles a second-order phase transition. What you can see is a small change in the baseline, meaning a small change in the heat capacity of the sample. This is what we call the glass transition temperature, Tg. Next, you keep heating your supercooled liquid. Viscosity will decrease with the increase in temperature, and at a certain temperature, atoms will have enough mobility to go to the most stable thermodynamic phase at that temperature, the crystal. At the temperature denoted Tx in the figure, glass starts to crystallize. Above that temperature, what you have is in your crucible are crystals. Crystals that will start to melt at Tf temperature. This peak of the endothermic melting event is called the melting temperature, or Tm. There is a third experimental observation, from some experimental techniques we must say, that may be used in the characterization of what we call a glass. These are spectroscopic techniques. Glasses are amorphous, and for that, a distribution of bond distances and angles are expected. Any spectroscopic technique sensing bond distances and angles will display broadened lines. This is the so-called inhomogeneous broadening, of spectral lines: vibrational spectroscopy, infrared absorption or Raman scattering, electronic spectroscopy, electron paramagnetic spectroscopy, EPR, nuclear magnetic spectroscopy, NMR. All these techniques are sensitive to bond distances and angles, and for that, we will always observe broadening of spectral lines with respect to crystals. However, even with broadened lines, the spectroscopic study of glasses can bring us a lot of useful information about the glass structure, which we do not know, since we are dealing with amorphous material. This is an example, not very recent but important. In this paper from 1982, these authors presented vibrational spectra for glasses and crystalline counterparts. The figure shows Raman spectra obtained for potassium silicate, crystal and glass. Bands appear broadened for the glass, but at about the same positions of the bands observed for the crystal. The observation suggests similarities for crystal and glass structures. One can therefore take the crystal structure as initial point in the description of the glass structure. This is very useful, for example, in generating a glass structure by methods like molecular dynamics, for example. This story goes further in importance. Different molecular structures may be identified in the glass medium. This figure is still taken from the same paper, shows the identification of metasilicate and disilicate structures. The polymerization degree of the inorganic structure may therefore be studied. These are results obtained in our lab some years ago. Crystalline lead germanate is isomorphous with the silicate mineral alamosite, lead silicate, which is described by unbranched linear metasilicate chains. Some years ago, Luciano Bueno was trying to synthesize lead germanate, pure phase, by classic solid-state reactions. By classic, I mean mixing lead oxide and germanium oxide precursors, long comminution in a mortar, pressing in pellets, and long heat treatments at temperatures given by phase diagrams, where the only stable phase was this lead germanate. Even with heat treatments of some days, he always obtained a mixture of different lead germanates with different formula. An interesting observation with important conclusions was made by Luciano. He prepared a glass with the composition lead germanate. He obtained the Raman spectra shown here. Broaded bands are around at the same position as the ones obtained for the crystal, suggesting similarities of structures. Okay, he then crystallized the glass at temperatures above Tg for some minutes. What did he obtain? The pure alamosite-like lead germanate he was trying to obtain with classic ceramic methods. What was the obvious conclusion? Two main conclusions, in fact. One, the unknown structure of the glass should closely resemble the structure of the crystal. And two, pure crystalline phases, otherwise difficult to be obtained, could be easily obtained in minutes by crystallizing a glass of the same composition. We can therefore describe the general picture we obtain from vibrational spectra. Vibrational modes are the same for crystals and glasses. However, due to the amorphous nature, dispersion is observed for the atomic distances and bond angles. Vibrational modes will be therefore affected. A dispersion is observed for the characteristic frequencies. Lines will be homogeneously broadened. The same holds for EPR, NMR, electronic spectra, etc. So, we have seen so far some experimental evidences that allow us to distinguish between a glass and a crystal. How does a glass form, anyway? We know that glasses have been made since 5000 years BC. Recipes, however, began to appear later. The first recipe known appeared in the famous Encyclopédie by Diderot and d'Alembert. The Encyclopédie, or Dictionnaire raisonné des sciences, des arts et des métiers, was a 28 volumes general encyclopedia published in France between 1752 and 1772 and edited by Denis Diderot and Jean-Léon d'Alembert. It was the first encyclopedia to include contributions from many named contributors, including Diderot, Voltaire, Rousseau, and Montesquieu. According to Diderot, the encyclopedia aim was to change the way people think, incorporating all of the world's knowledge and representing the thought of the Enlightenment, which was a cultural movement of intellectuals in the 17th and 18th century. The purpose of the movement was to reform society using reason to challenge ideas grounded in traditions and faith, and advance knowledge through the scientific methods. Interesting the goals of these guys, aren't they? It is fantastic that the movement could begin today again. We need someone with this clarity in mind. What do you think? But let's for a moment leave the Enlightenment and come back to glasses. In this encyclopedia, we find the recipe to make a glass. All you need is some sand, silica, lime, and soda. Take to a high temperature, quench the melt, and you will have a glass. For those interested in archaeology and glassworking, at the school website you will find this document, Archaeological Evidence for Glassworking. We got from the Customer Service Department, English Heritage website. It has nothing to do with materials for photonics, but it's an interesting document to take a look concerning the historical facts about glass making. In fact, the story is much older. Natural glasses has existed since the beginnings of time. Melting of rocks as a result of high-temperature phenomena, volcanic eruptions, lightning strikes, or the impact of meteorites, cool and solidify rapidly. Obsidians are natural glasses of volcanic origin. Stone Age men used cutting tools made of obsidians. They are black because of the iron content. Probably you've seen Game of Thrones. This is a link to a short YouTube movie showing the moment that Sam finds a box with dragon glass knives. With this dragon glass knife, and only with that, he could kill someone from the Dead's army. I do not know if the dragon glass was that powerful, but one thing we know, it was made with obsidian glass. The evolution of the glass's story since almost 5,000 years BC can be more or less summarized like that. 4500 BC, the accidental finding. Phoenician fishermen observed the formation of glasses on the fires from the mixture of sand and ashes under high temperature. 2500 BC, Egypt. Glass preparation methodology was established. Basically the very same method we use today, from sand and ashes. 1500 years BC, the oldest fragments of glass vases were found in Mesopotamia. 650 BC, first glass-making manual, instructions on how to make glasses, on tablets from the library of the Assyrian king Ashurbanipal. 30 BC until 15 AD, the glass-blowing techniques were established. Syrian craftsmen from the Sidon-Babylon area. Ancient Romans, 1 BC, began blowing glasses inside molds, increasing the variety of possible shapes. After that, Romans spread out glass in Europe, Italy, France, Germany, Switzerland, and even China, shipped there along the Silk Roads. Romans also introduced glass for architectural purposes. Clear glass was produced in Alexandria, 100 AD. Cast glass windows in important buildings are found in Rome, Herculaneum, and Pompeii. Going further, In time, in the Middle Age, the glass-making center of the Western world was established in Venice and Murano Islands. Even today, tourists in Italy can visit glass-making atelier in Murano. It's a nice place to visit. The lead crystal we have already mentioned. As you know, it's not a crystalline material. It's a glass with high content of lead. Because of the high content of lead, it's brilliant. You remember that. Lead increases the refractive index, giving the brilliant aspect. Lead also lowers the viscosity, allowing easy deep cutting and engraving. After that, we have some glass makers you probably have heard about. The telescope and lenses developed by Galileo, the mirrors, lenses, and prisms developed by Newton, and all the lab glassware developed by the alchemists. These are some more images from the encyclopedia. To understand the caption, you will need to practice your French. From 2 centuries to now, we had in the 19th century the important work of Otto Schott in Germany, who is considered to be the father of modern glass research. From his work, scientific methods were developed to evaluate the effects of numerous chemical elements on the optical and thermal properties of glass. The Carl Zeiss Company was born in Germany. Zeiss was an optical and precision mechanics specialist, and founded an optical workshop in Jena in 1846 producing microscopes. In 1866, Zeiss met Ernst Abbe, who became a partner of his business in 1875. Ernst Abbe proposed the theory of optical imaging of the microscope that established him as the founder of the scientific optics. His theory, combined with new optical materials from Otto Schott, gave the Zeiss Company an enormous technological advantage. The collaboration between Zeiss, Abbe, and Schott enabled large-scale production of high-powered microscopes in uniform quality. Another important actor in glass industry was born in 1853 in US. The two German immigrants, John Jacob Bosch and Henry C. Lomb, founded the Bosch and Lomb Company, initially producing microscopes, photographic lenses, spectacle lenses, microtomes, binoculars, and telescopes. Nowadays, the main business of the company are contact lenses and eye health products. If you are a big fan like myself of Ray-Ban sunglasses, you must know that they are not a Bosch Lomb product anymore. The brand was sold to an Italian group in 1999. In the 20th century, mass production started. A big technological development was achieved after the Second World War. While the 19th century development was mainly based on trial and error, research and technology are now considered together in the 20th century and in the 21st century as well. The conference, which brings the state of the art in glass science, is organized every 3 years by ICG, the International Commission on Glass. These are the icons of the last three conferences: in 2007 in Strasbourg, France, in 2010 here in Brazil, in Bahia State, and in 2013 in Prague, Czech Republic. The next one will be held in Shanghai, China, next year. Perhaps we will meet there for a Chinese beer. Who knows? Well, coming back to glasses preparation, this table shows the chemical composition of some known glasses, from bottles to lamp bulbs, and all compositions are based on silica. Other components are added to the glass batch to adjust properties. Just to start to talk about some optical properties, take a look at the chemical composition of what we call crystal, as we have already mentioned. This name brings some confusion to the field, but a crystal glass is not crystalline. It is a glass, amorphous. Its name comes from the brilliance that is due to the high refractive index. The high refractive index is due to the almost 30% of lead oxide added to the glass composition. The refractive index of ordinary glass is around 1.5, while with the addition of lead oxide the value of 1.7 may be achieved. In fact, these glasses with high lead content are called lead crystals. The addition of lead oxide also lowers working temperature and viscosity, which brings advantages in the glass production, of course. Due to environmental problems, glass companies work looking for a substitute for lead oxide. Niobium oxide is a good option. At the school website you will find a report from a Japanese company, Ohara, on this subject. The preparation method of glasses, established almost 7,000 years ago, may be summarized in this picture. The figure shows the variation of the specific volume as a function of the temperature. It could be the enthalpy as a function of the temperature in the same way. Starting from the liquid at high temperature, cooling down leads to a decrease of the volume for most of the substances. A small parenthesis here. Water is an exception. The volume occupied by the solid is larger than the volume occupied by the liquid. You know that. But have you ever thought about that property of water? If it was not like this, life could not exist on Earth. Well, coming back to the scheme for a normal substance. If the cooling is done slowly enough, in a way that nucleation and growth process could occur, a first-order transition will occur, and a crystalline solid is formed at the thermodynamic transition temperature, defined as Tf in the plot. Volume will discontinuously decrease, and after that, further cooling will lead to the decrease in the volume in a different rate. However, lacking any nuclei, the liquid phase can be maintained at temperatures below Tf. In fact, every liquid can be found in a supercooled state. Of how many degrees under Tf may be the liquid cooled, it will depend on the liquid viscosity, and the viscosity will depend on the liquid structure, which we do not know, by the way. Water, for example, can be supercooled a few degrees below Tf. Melted silica, highly viscous, can be supercooled thousands of degrees. In the plot, by cooling the supercooled liquid, viscosity increases. When viscosity is around 10 to the 12 Pascal second, the material starts to behave like a solid. This is the transition from the viscous supercooled liquid to the solid. In this case, an amorphous solid, a glass. We call this temperature the glass transition temperature. Cooling further, the volume will decrease at a rate similar to the crystal. Several definitions exist for a glass. The American Society for Testing in Materials defines a glass as an inorganic product of melting, which has cooled to a rigid condition without crystallizing. This is, of course, a very restrictive definition, since organic compounds also form glasses. Moreover, several other methods exist besides cooling down melt. In textbooks, you will find other definitions: amorphous solids, undercooled liquids, amorphous solids displaying Tg. This is the most used definition, by the way. Gutsov, in his book The Vitreous State, gives a very general definition. A glass can be any state, thermodynamically metastable, with frozen-in properties. I have borrowed these next slides from my dear friend Austin Angel from Arizona State University. Professor Angel is one of the most important and known specialists in glass science. His clarity in his talks is impressive. And after a class he gave here in Brazil to our undergrad students in 2007, I took these very pedagogical schemes from him, with his authorization, of course. This is an energy diagram, a ball in a bowl scheme, showing the way down from a high energy state to a lowest rest energy state. The system may be in a high energy trap, a metastable state. In order to go down to the lowest state, the system must get some energy to climb the barrier. The very same scheme can be used to show the energy difference between the glass and the crystal. The difference in energy is the energy released in crystallization. The difference in energy between the glass and the liquid is given by the energy of heating that can be known given the heat capacity. Once obtained by quenching the melt, it's a common practice in glass production to bring the glass to a high temperature again, below Tg, in order to relax. Annealing is a routine operation in the preparation of glasses. The structure needs to mechanically relax. A common observation from non-experienced glassmakers is the shatter of a glass piece due to wrong, not slow enough, cooling operations. This is the link for a short movie produced by the Corning Museum of Glass in US, where we will see the effects of annealing or not a piece of glass. Take a look at it. It's very interesting. You will see that the optical properties of a glass submitted to mechanical stress are different from the properties of a well-prepared glass. This is, of course, a very, very important observation concerning our course. Take a look again at the plot of the volume as a function of the temperature made by Professor Angel. The metastable state of glasses, unhappy phase, is shown here to appear when cooling the supercooled liquid under Tg. You must agree with me that the unhappy phase cannot be due to the fact that it is a glass. Concerning the potential applications, the spread use, and the infinite possibilities, it should be very happy, in fact. Thus, another interesting scheme made by Professor Angel shows the diversity of metastable states possible. In fact, despite the unknown glass structure, we do know, and again this is very important concerning optical properties, that several metastable situations are possible. The trick to obtain a good glass is to find the lowest energy one. At this point, we can call your attention to the puzzle related to the glass preparation. When cooling from the melt, the volume decreases, and at a certain temperature a glass is obtained. The decrease in volume is important, but not that important. The fluidity, however, decreases by orders of magnitude, as shown in the plot. A good explanation for this puzzle is still lacking. In fact, if you take a look at some viscosity values at Tf for some liquids, you will see a remarkable variation. Some liquids are very viscous at Tf as silica, while others are not as water. The liquids presenting viscosity values above 10 to the 5 boas at Tf are known to be what we call good glass formers, because glasses are easily obtained from them. To those of you who never saw silica at the melting point, I must say that 10 to the 7 is the viscosity of a good honey. This plot gives us a better general view of the situation. It is a TTT plot, that is, temperature against time. It's an empirical plot, a very difficult and laborious experimental measurement. Starting from a high temperature, the plot shows the time to get a small fraction of crystallization at a temperature below Tf. You see that, in this region, the lower the temperature, the lower the time to get crystals, according to the thermodynamic tendency to go to the more stable crystal. However, for even lower temperatures, the situation changes surprisingly. The time to get crystals increases for lower temperatures. Here you must consider that, in parallel with the increasing thermodynamic tendency to crystallize as the temperature goes down, the viscosity dramatically increases. The increase in the viscosity hinders the crystallization due to the lower mobility of the species. These opposite effects, playing on the supercooled liquid, give this nose form to the plot. The important point here is that when preparing a glass, the glassmaker must pass fast through this temperature range, defined by the nose. Otherwise, the liquid will crystallize. Therefore, an important information given by this figure to the glassmaker are the coordinates of the nose tips. The so-called critical cooling rate and thickness can be obtained from them. In this table, you have some typical values for critical cooling rate and thickness. Silica is in fact a good glass former. In practice, it's easier to obtain amorphous silica than the crystalline form. Germanium oxide is also a good glass former. For water, the situation is completely different. In order to obtain water glass, special cooling techniques are required, and even though the thickness is restricted to 1 micron. Metallic glass also exists, but cooling techniques even more efficient are required. However, even with this special cooling technique, you will only obtain a thin film of metal glass. This plot shows the viscosity values of a molten soda-lime silica glass as a function of the temperature. You can see it follows an Arrhenian behavior. On the plot, you see characteristic temperatures used in glass technology, all based therefore on viscosity values. These are: the melting or fining point is the temperature at which the viscosity value is around 100 poise. At the working point or forming point, the viscosity is 10 to the 4 poise. At the softening temperature, the viscosity is 10 to the 7.65 poise. The annealing point is usually defined as the Tg temperature, that is, the viscosity is 10 to the 13 poise. And finally, the strain point, where the viscosity is 10 to the 14.5 poise. At this temperature, the glass is still too hard to deform, but is soft enough for the stress to relax. We have already commented on the need of annealing in order to release stress. This stress release occurs in some minutes if annealing is performed at Tg, and in some hours if performed at the strain point. This figure gathers results for viscosities for a large number of substances. You see that some of them follow an Arrhenian behavior, like silica and germania, while others don't. Professor Angel proposed to scale the plot using Tg. By doing this, the glasses obeying or not the Arrhenian behavior can be easily distinguished. In fact, Professor Angel proposed the classification of glass on the basis of that behavior. Strong glasses are the glasses following an Arrhenian behavior, while fragile glasses don't. Therefore, after all this discussion, we can say that glasses are amorphous materials displaying Tg, even though sometimes it can be difficult to identify Tg. In this table, you have some values for Tg and Tf for some glass formers. The ratio Tg over Tm is usually used to classify glass formers. It's experimentally observed that this ratio falls in the range of 2/3 for good glass formers. Just to reinforce the idea, this is again the DSC plot for a typical glass, with the characteristic thermal events that characterize in fact the glasses. In our definition, glass is amorphous displaying Tg. Tg is easily distinguished in the plot. Concerning methods to prepare glasses, this figure shows some cooling methods for increasing cooling rates from left to right. By increasing the cooling rate, we can prepare glasses from melts that by conventional cooling could not be obtained. Slow cooling concerns leaving the sample to cool from the melt temperature to room temperature at the cooling rate of the furnace. Moderate cooling rate can be achieved, for example, by cooling the melt in water. An anvil and a piston may be used to increase cooling rate, while in the condensation from the vapor you can cool even faster. Even metal samples can be obtained as glasses, provided a very fast cooling rate. This kind of device is used to obtain metallic glasses by the methods we call melt spinning. The solid ribbon of amorphous metal is spun off at speeds that can exceed 1 km per minute. In this slide you have a 15 seconds movie showing this process. The message to be kept here is that the formation or not of a glass is in fact a kinetic process. However, we still use to classify substances in glass formers and glass modifiers. Glass formers are capable of forming three-dimensional structures from basic structural units. The main characteristic is the low coordination numbers for the cations. Modifiers, big cations that do not take place in the polymerized network. They lower melting temperatures as the network depolymerizes, that is, bonds involving bridging oxygens are broken. This scheme shows two SiO4 tetrahedra sharing one oxygen. It is the bridging oxygens. The introduction of alkali breaks the bond, leading to two non-bridging oxygens. It's more or less clear that the higher the number of bridging oxygen atoms, that is, the higher the polymerization degree, the highest will be the melting temperature and the viscosity of the liquid. Here again we have the famous 2D Zachariasen random network. We can also observe bridging and non-bridging oxygens here. Therefore, obtaining a glass or an amorphous solid is supposed to be a way of keeping at room temperature the disordered state typical of gases and liquids. Alternatively, one can destroy the ordered structure of a crystal, as we have already shown in the case of lead germanate. We can therefore obtain glasses from liquids, gases, and solids. A survey of methods for preparing non-crystalline solids is given in this scheme. As we've seen, glasses are obtained by sufficiently rapid cooling or quenching of melts. Glasses can also be obtained by drying gels from solutions. Processes of precipitation from solutions often lead to amorphous precipitates, as in the case of red amorphous selenium, sulfides of arsenic, antimony, germanium, tin, and numerous other metals or metals hydroxides. Electrolytic separation using a high current density leads to amorphous layers, such as amorphous germanium. The first examples of metallic glasses were obtained by this means. With regard to methods starting from the gas phase, the most important of these are the several variants of thermal evaporation and condensation, in high vacuum, cathode sputtering, and deposition of amorphous layers in glow discharge processes. Reactive vapor deposition is important in the formation of vitrosilica or amorphous silica layers through hydrolysis of silicon chloride or through pyrolysis of silicon chloride oxygen mixtures. Vitrosilica films or silica layers can also be generated by the direct oxidation of silicon monocrystals at the surface. Also, crystalline solids are converted to the amorphous states by the influence of shock waves or intense irradiation with neutrons or ions. Amorphous states are often formed during solid-state decomposition reactions, such as the dehydration of kaolinite. Finally, as already seen here, the mechanical treatment of crystalline solids, such as grinding and polishing, also leads to strongly disordered and amorphous surface layer. Of course, an awareness of these reactions is essential for some important technological processes. The black dot arrows in the inner circle of the figure indicate that by a suitable choice of preparation conditions or by subsequent annealing, The amorphous films and layers can be converted to a modification very close to that of compact glasses, such as the ones obtained from a melt. Glasses can be classified in families: oxides, metallic, halides, chalcogenides, and organic glasses are the main families. Take a look at this YouTube movie to learn how to prepare a sugar glass. Or you can take a look at this other YouTube movie to see the amazing properties metal glasses can present. The classification of substances may be done based on structural approaches, for example, crystallographic concepts. The Goldschmidt ratio is an old concept in inorganic chemistry related to the ratio of the cation radius to the anion radius. The Goldschmidt ratio allows one to preview polyhedral formed as a function of the relative sizes of cations and anions. Nc in the figure is the number of coordination. It turns out that glass formers fall in the region of Nc equals 4. Therefore, this is one of the first criteria proposed to classify a substance as glass former. Zachariasen, in his famous paper of 1932, also proposed some rules that would allow the formation of his continuous random network. The rules are like this: low coordination number polyhedra, the number of vertices must be lower than 6. Polyhedra must be connected by vertices. Anions do not connect to more than 2 central ions. These oxides satisfy Zachariasen rules. In fact, glasses are known for some of them. Following Zachariasen rules, this table shows formers, modifiers, and some intermediate ones. Another approach used to classify substances is related to the chemical bonds. Therefore, one can obtain glasses from inorganic compounds displaying partially ionic and partially covalent bonds, like silica, boron oxide, etc. Elements in which structure long covalent chains interact by weak van der Waals bonds, such as sulfur and selenium, and organic compounds with strong intramolecular covalent bonds and weak van der Waals intermolecular interactions, as in sugar. The Stanworth criteria are based on the percent ionic character of a chemical bond. The stronger the ionic character, the lower will be the tendency to form a glass. This is a plot showing the percent of ionic character in a covalent bond as a function of the electronegativity difference between two atoms, considering the electronegativity of the oxygen as 3.4. Formers will be the substances where the difference between the electronegativity of the oxygen and the metal falls in the range of 0.6 to 1.6. Modifiers will be those with values between 2.2 and 2.7, and intermediates those with values between 1.7 and 1.9. And finally, the relationship of vitrification and bond strength. The Sun's criteria is based on the dissociation energy, ED, and the coordination number, CN. It is some kind of distribution of the bonding energy by the number of bonds. Glass formers will present high values for this B parameter. Again, formers, modifiers, and intermediates can be separated. To finish this class, here we have the Rawson criteria. Rawson took Sun's criteria B and divided by the melting temperatures. It is the evaluation in a certain way of the available thermal energy. The higher the value, the higher the tendency to be a glass former. So let's finish this class with some images of Amazon, an astonishing region in Brazil. Don't forget to answer the quizzes. See you next class.